I love fluids and studying fluid dynamics. I especially love splashes. I am fascinated by the geometry water takes when an object is dropped into it. So when we were given this assignment, I knew I wanted to do something with splashes. We had the question, is there a correlation between the coefficient of drag and the height of a splash?
Unfortunately, we couldn't find anything that directly answered our question. Preliminary research, however, led me to a document by Jameson Lawrence Toole called Experiments in Splashing. In his paper, Toole describes using dimensional analysis with the parameters of the Navier-Stokes equations, coming out to the four equations shown here. Through his own experiments, he discovered a link between viscosity and surface tension of a fluid through inertial forces, and how the Weber number and the Reynolds number of a fluid determine the general shape of a splash. From Toole's work, we can break down a splash's anatomy to determine what we were looking for in our own experiments. So let's break down what's happening here. As the sphere drops down into the fluid, we see a cavity begin to form behind it. This cavity continues to extend until pinching off due to pressure forces. Once the upper cavity has been cut off from the momentum of the object, it collapses upward, extending far above the surface to create a taller secondary splash. Breaking down the anatomy of the splash itself, we can see that it is made up of two separate parts: the crown, which is where the water still forms a continuous surface, and the microdroplets, where the fluid has begun to break apart. After running some of our own experiments, we delved deeper into some other research.
From our other research, we were able to find out about what other properties of the falling object and also the water affect the splash behavior. The more hydrophobic an object is, we learned that it'll create a smoother crown from the initial impact, and it'll also create a smoother surface for the cavity. When it's more hydrophilic, those are a little bit less defined and a little bumpy as well. Also, we found out that with atmospheric pressure, when it's reduced, it will make it so the crown seal does not happen as much. And that seal can be seen in the images to the right, where the crown comes up onto itself. And when this seal happens, it prevents the secondary splash from really occurring because it runs into the seal. So the lower the atmospheric pressure is, the less likely there is for a seal to form. And if the seal doesn't form, you can see the secondary splash happen. Also found out that the Reynolds number of the fluid will affect when it turns into microdroplets. The higher the Reynolds number, the more microdroplets will occur sooner. And also the Weber number influences the geometry of those droplets. That the higher that Weber number is, the more non-spherical the droplets become. Also, we found out that the Froude number of the object falling also impacts how the splash behaves, particularly what the size of the object is and how fast it impacts the water. And a higher Froude number leads to a bigger cavity and a greater tendency for the crown to seal from splashing. We also found how some of these factors related to the splash height, particularly the front area of the object impacting the water will create bigger cavities, which will create bigger splashes. The impacting velocity, as this increases, it also does the same effect as increasing the frontal area. Also, the water depth is important to the splash, because if the water depth is not as deep as the cavity from the impact is, then the splash will not be as large as it could be. So you will not get as much height out of the splash. But if the water is deeper than this cavity, it doesn't affect the splash much anymore. Also, as talked before, decreasing the air density will cause there to be bigger splash as well.
The video on the right is one of dozens of videos we took experimenting dropping objects with different coefficients of drag. Our inability to find a direct correlation showed the complexity of splashes. However, we enjoyed learning from other more rigorous studies about the anatomy of splashes as well as the factors in splash behavior. Finally, here are a few more videos collected from our experiments.